That last video had a parametric example that had some kind of weirdness going on, right? So most of the time we don't have to worry so much about those weird things, but I thought I'd show them to you just in case they crop their heads somewhere. This is going to be a much more standard sort of question. Take a look at x equals 4 cosine t, y equals 4 sine t. You should recognize this. Remember, if you divide both sides by 4, you get cosine of t. If you divide both sides by 4, you get sine of t. Using our favorite trig identity, we can turn this into a rectangular equation. And notice that, ironically, your rectangular equation gives you a circle. But at any rate, the question is, can you find the points of horizontal and vertical tangency on a circle? Well, that's pretty easy if you are thinking about it graphically, right? Just think about, okay, we've got a radius of 4, so it's pretty clear where our points of tangency are going to be. Horizontal are going to be 0, 4, and 0, negative 4, right? And vertical, they're going to be 4, 0, and negative 4, 0. So hey, if you're on a multiple choice question that you don't have to show your steps, boom, you're done. Spend 5 seconds on this question and move on. But if you're going to expect it to show your work on this, then at the very least we know what the answer will be. So when we work this out, we won't be surprised. And if we get something different, we can find our mistake. So remember that horizontal points of tangency are when dy dt equals 0 and dx dt does not equal 0, right? Sometimes people forget which is which, but if we're just thinking about horizontal, we know that the slope has to equal 0. And 0 can be had from 0 divided by a non-zero number. So if we know the basics of slopes, then that shouldn't be a problem. All right, so we're going to find dy dt. Well, that's easy enough. Dy dt equals 4 times the cosine of t, right? Sine differentiates to cosine. Dx dt is going to equal negative, right? Cosine is negative. Cosine goes to negative. Sine, negative 4 sine of t. All right, so in practice, we don't worry about setting this not equal to 0 because there are lots and lots of t values that will cause this to not equal 0. So let's find the potential values over here. And of course, there's going to be a lot of answers because this is a trig question. So we've got cosine equals 0 when the angle is pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, or negative pi over 2, etc. There are lots and lots of answers. Okay, but you'll notice that these values right here cause the sign to equal something other than 0, right? Either positive or negative 1 in this case. So all of these are good cases. We don't have to worry about throwing anything out, like we had to throw away the t equals 1 in that last problem. We don't have to throw anything out, and we'll just pick the values here. And notice that, as we circle around the circle, we are just going to keep on hitting the same points over and over again. So really all we need is 2 values. We need these 2 values right here. So we're going to have x equals, or t equals pi over 2, rather, is going to give us the point, well, pi over 2 has a cosine of 0, right? And pi over 2 has a sine of 1, so 4 times 1 is 4. Oh, what a surprise. 0, 4 is one of the points of horizontal tangency. And then when we do the same thing with t equals 3 pi over 2, of course, we're going to get the bottom point. So let's just fill those in, and then we'll just quickly, come on. All right, so those are the 2 points of horizontal tangency. Now, if we want to try the vertical points of tangency, that's when dx dt is going to equal 0, and dy dt does not equal 0, right? And again, don't get confused by this. Vertical tangencies means the slope is undefined, and that happens when we get a non-zero number on the top and 0 on the bottom. When our rise is something and our run is nothing, we have a vertical tangent line. So that's when we're going to set dx dt, or negative 4 sine of t, equal to 0. we want to make sure that, we'll go ahead and label this as dx dt. We want to make sure that dy dt is not equal to 0. dy dt, as we already talked about, is 4 times the cosine of t. So we're going to set this equal to 0. We're going to find that sine of t equals 0 when t equals 0, and pi, and 2 pi, and 3 pi, and 4 pi, and the other direction with negative pi and negative 2 pi, all that jazz, right? So again, we're just going to worry about two of these values, t equals 0 and t equals pi. When t equals 0, we get the point 4 comma 0. When t equals pi, we get the point negative 4 comma 0. And those are the points that have a vertical tangent line. All right, so it's nice to see that the messy, tedious calculus method here works out, but the elegant, quick, intuitive way to do this problem is also a very good way to think of it. All right, so what if we have something that is not quite so intuitive and we just have to jump into the calculus? All right, well, this looks an awful lot like that first one that had that sharp turn, doesn't it, right? I think I changed the -2 to a +2, and I got rid of the coefficient of 2 and the coefficient of 3. So other than that, it's the same graph. So there's some similarities in here for sure. So let's first find the horizontal points of tangency. So that's, we're going to set dy dt equal to 0. So dy dt is equal to 3t squared minus 1. Some old power rule business, right? And we'll set that equal to 0. We'll get t equals plus or minus the square root of 1/3. Or if you prefer to rationalize, plus or minus the square root of 3 over 3. All right, well, we should probably double check to make sure that the other guy, which is the vertical point of tangency stuff, the dx dt, we better make sure that that one doesn't equal 0 for these guys. So let's just double check. Remember that we did have that situation on the warm-up on that first example. So dx dt is equal to 2t minus 1, and if we set that equal to 0, we don't get either of these two values. We get a whole new value of t equals 1/2. So we don't ever get the indeterminate 0 over 0 like we did on that other example. So all we need to do is take those values and plug them in for x and y. So, or no, in to solve for x and y rather. So if t equals, let's start with the negative square root of 1/3. We get, well, we're going to square that to get 1/3 minus a negative square root of 1/3 plus 2, comma, and then we'll do the same thing over here with this one. We're going to cube the square root of 1/3, and that's going to give us negative 1 over 3 root 3, and then minus a negative, so that's going to be plus 1 over root 3. So this will simplify a bit, and we'll get some kind of messy answer like 4/3 plus 1 over root 3, comma, let's get a common denominator here, a 3 on the bottom and a 3 on the top. 3 minus 1 is 2, 2 over 3 root 3. That's one of the points of horizontal tangency. To find the other one, when we do t equals positive the square root of 1/3, just do the same thing. We'll get positive 1/3 again. This time will be minus 1 over root 3 plus 2. And then this should be the same thing, just with the opposite signs. This is an odd function, so change the sign of the input, you'll change the sign of the output. So I'm just going to jump straight to negative 2 over 3 root 3. Save a bit of calculation time there. We still get 4/3 for the constant, or the for the rational part of the x value. We just have a minus in there instead of a plus for the irrational part of the x coordinate. And again, the y value switches from positive to negative. All right, so those are our 2 points that have a horizontal tangent line. I don't like that. Let's not box that in because it was getting messy. And now we'll go ahead and find that 1 point of vertical tangency. That's going to be when t equals 1/2. So this is just a bunch of algebra, right? We get 1/2 squared minus 1/2 plus 2, 1/2 cubed minus 1/2, and we just work it out. We can work it out. So we've got, let's see, 8/4 minus 2/4. 8 minus 2 is 6. 6 plus 1 is 7. That's 7/4. And 1/8 minus 1/2 is the same thing as minus 4/8, which is 1 minus 4 is -3. So that should be what we end up with for our vertical point of tangency. All right, so I can't resist. I got to check this in Desmos. So if you already have checked in Desmos, then you're like me. If you haven't seen that and you want to see it here, keep on watching because we'll go ahead and graph. You know what? Tell you what, you should pause this instead. Don't watch me do it. Do it yourself. And then check your answers. So pause the video and see if you can come up with the graph and the verification. All right, so I can't remember what we had. We had 4/3 plus 1/√3. 4/3 plus 1 over the square root of 3 was the x value, comma, the y value was 2/3√3. 2/3√3. Uh-oh, that's not good. That doesn't look like it's on the curve at all. I made a mistake, which makes me sad. Let's just double check this. Someone's watching this and says, oh, you forgot this. When will he notice the problem? But I'm not seeing it. I'm going to pause the video so you guys don't have to suffer through this. It's always the silly things, isn't it? I added 2 plus 1/3, but I pretended in my head I had 1 plus 1/3, so this should be a 7 instead. So we'll change that to a 7. Same thing over here. So hopefully, if all goes well, if I just change that to a 7 instead of a 4, we'll see a point on the curve. Aha! Not only is it a point on the curve, it seems to be a point of horizontal tangency. All right, now take a look at this curve. Doesn't this look an awful lot like that kind of folded parabola type shape that we saw in the first example? But apparently we have another horizontal point of tangency. So I know it was very similar to this. We just had to change this to a minus, a negative, and change also this to a minus, negative. All right, so, okay, well, it's a little hard to tell, but what if we zoom in on this? Whoops, I don't want to distort it. Hold on. If we zoom in on this, oh my goodness, look. It's a little loop-de-loop, like that cycloid thing. And if we zoom in on this point, it sure does look like that's a point where there's a horizontal tangent line. Oh, that's exciting. Okay, so it's always really great when we double check these things and they work out. Not only that, but we also have, it appears very close to that point, a place where there's a vertical point of tangency, and that's the much more friendly point, 7/4, comma, -3/8. If I didn't make any mistakes, 7/4, comma, -3/8. All right, now I can't even see my green one anymore, so we better zoom in and see if my green one's still there. It's still there, but take a look. Take a look at that purple one. It's exactly where we want it to be, right where there's a vertical point of tangency, right? That vertical tangent line right there. This is perfect. So, and that's the only time that happens, right? There's no other place where we have a vertical tangent line. It might get steeper, but it never gets super steep. It never gets vertically steep, infinitely steep. So there we found all 3 of those special points, and 2 of them are outstandingly close to each other.